Engineering 305, problem 222. Isn't this awesome? Isn't it? I mean, this is just awesome. This is what we did. Gotta get rid of the mask. This is what we did last week. Whenever you did it. This is awesome. So we get to do it again. Here's the problem. Problem statement. First thing we got to look at, problem statement. A pair of vice grip pliers is shown in figure P2-22. Or you could go back, it was problem 1-70. When a force of P equals to 100 newtons, that seems like it's about exactly what we had last time, is being applied to the handles. It really looks like the same picture. They should have just said it's a repeat. Determine or find the average shearing stress in the pin at A if it has a 4 millimeter diameter and it's in double shear. And find B, the second thing we've got to find is the average shearing stress in the pin B if it has a 5 millimeter diameter and is in double shear. Okay, cool. So what is it that we have we've got our problem statement, we've got our finds, there's some givens in there we'll work with as we go through. Key things, probably double shear, that these things are have shear on both sides of the pin. So depending on how you think about that, either you have twice the area or you have half the load. The equation works out the same either way. What else do we know? What other givens do we have? Well, how about this? We already solved this problem. We already know. This is where we ended up. This is the solution from 170. I had a reaction force. This is the free body diagram for that front piece. I had a force here, 788 newtons. I had a force vertical, 372. I never did anything to calculate the reaction forces at B. I did not do that. And then I've got a force on that little nugget of 842 newtons. And I had some geometry. That I knew. I guess I have one more piece here. I got distracted. The length of the hypotenuse, in case you want to do it with that technique, the length of the hypotenuse is 38.1. That came out of that other problem too. Cool. So the first thing we were supposed to find, I want to know shear average at A. Well, that's equal to V over A. It's in double shear. So as I said, it's either half the load, which would be V over 2, or I get twice the area. It shows up the same. This is double shear. Double shear. All right? Yeah. What's V? This is what I'm solving for, so I must know V and I must know A. Otherwise, so what's my shear? Well, I actually didn't solve for this in problem 170. I have the components, 788 and 372. So it would be that shear force is going to be equal to the square root of 788 squared plus 372 squared. Put my 2 back in there. And then my area, I go back to my problem statement. That pin is a 4 millimeter pin at A. Pin's a 4 millimeter pin. So my area, sorry, let me go back to that one more time. 4 millimeter, diameter. 4 millimeter diameter. So that is going to be equal to, the area is pi times d squared over 4. I put that in meters. Why? Because my units are going to be in pascals, which is newtons per meter squared. And when you start dealing with meters squared, and then you're going to have, if you did it in millimeters, it would be to the 6th power, because it would be millimeters. It's easiest for me to think about And that doesn't mean that it's the right solution for you. You've got to think about some of those things yourself. All right, we'll start simplifying that. Hold on. Oh, I paused it to do the calculations because I don't think that makes for good television. Honestly, I just don't think that really makes for good television. And I didn't have it handy in front of me. So that turns into the 872 newtons. I wanted that separate. I think that might come in handy for part B. I don't remember. And then I just calculated out the area, double area, 25.12 E negative 6 meters squared, which gives me 34.7 megapascals in that pin. That's my shear. And then I should highlight that. All right, on to part B. On to part B, which now really, to do part B, I guess I still need this piece of paper. I never found my reaction forces here. I never found the reaction forces there. And that's got to be my next step. Now, I'm trying to think about how the best way to attack that would be. Can I do, if I did a sum of the moments about A, and I had that, but I don't know the line of action, and if I knew, and I don't know the line of action, and I don't know the distance, so I still have a couple variables there. I think I'm still stuck. I'm going to have to solve for Bx and By, and so maybe the easiest way to do that is just sum of the forces in the x direction are equal to, put this over here, sum of the forces in the x direction are equal to a positive 788 and then plus b in the x direction and a minus 842, and then that portion of that that's going that way, well, we can do that. Really, it's this angle. If I want to think about it, it's that angle that I'm interested in. It would be cosine of that angle, which would be, hold on, sorry, I had to sneeze. That angle would be the 15 using over the 38.1. It's the sine of this angle or the cosine of that angle. You got to sort that out. But here's the way. This is the other way I think about these problems, is I think about as this angle goes to this, does that become larger or smaller? Well, becomes, that height becomes smaller. It goes to 0, even though that stays the same. That's not the term, that is the term I'm looking for. As that comes that way, that's this will go to 0. It will all be in the vertical direction. None of it will be in the horizontal. So that's the term I'm looking for, the 15 over the 38. So put that there. I've got my equation. Those are all the forces that are acting. That one, that one, that one. And then I can solve that. The force at B in the x direction is equal to 456.5, 457 newtons, and that's a negative. Does that make sense? Well, yeah, that makes sense. This is pushing that way. This is pushing that way. There's only a little bit going that. No, that can't be. This has to be counteracting. There's a little bit from this going back, but this has to also be contributing that way. So it's a negative 457. Let's solve for B in the y direction. I just slid that off the page. I probably need that. Let's see if I can tuck it. We'll just put it there for now. It's all right. Some of the forces in the y direction are equal to, I've got 372 in the vertical direction. That's positive. I've got plus by. And then I also have plus 842. And now I got to get my trig again. It's going to be this. It's going to be 35 over 38.1. As this angle would go this way, then that would go to 1 as that angle goes down, and that would all be in the vertical direction. So it's 35 over the 38.1, which is the cosine of the angle. I know some of you are probably just laughing going, dude, just get your trig figured out. I know, that's all this is, but I'm giving people alternatives. If you don't want to, if you fight the trig or give yourself a different way to think about it, it allows me to think through, does it make sense? Cosine theta doesn't necessarily make sense. It may be automatic that I could do it. It may be automatic. But this is something I can logic through and come up with an answer. So now once I've got this one, some of the forces in the y, then I can calculate that by is equal to negative 1147 newtons. Negative, does that make sense? Does that make sense? Well, this is acting up and that's acting up. By's got to be down. Okay. So that's good. I like that. Now this is in x and y. So what I really need to do is find b. Well, that's square root of the sum of the squares of bx squared plus by squared. And so I do that calculation, and I'm going to get that this is actually equal to, and you kind of love this, 1, 2, 3, 4 newtons. And then I'm back to my shear equation. My shear is equal to V over, it's double shear, double shear. It's in our assumptions. It's either half the load or twice the area, is equal to 1, 2, 3, 4 over 2. And then this has a 5 millimeter pin. That's the difference about this one. So this is pi times 0.005 squared over 4. I'll put a couple parentheses around that so you can see this is, and I track my units, newtons, and that's going to be meters. So it's newtons per meter squared. So I do get MPa out of this. And the answer that I came up with was 31.4 is equal to the shear, and I'm going to label it at B. All right, cool. And I got to label this page in case anybody ever stumbles across it. I want you to know that this is problem 2-22. This is 1 of 2. And now I'll put this here. This is page 1 of 2. Well, let's look at this a second. I think this is pretty cool, and this is something that is why I think you should take time to reflect on these answers a little bit that you're getting. The shear in pin A is 34.7. The shear in pin B is 31.4. Let's assume that's actually the case. Let's assume that these numbers, this geometry, these definitions, and the problem came about from real world stuff. These two pins have been sized so that these stresses are roughly the same. They could have put a 5 millimeter pin and a 5 millimeter pin here, and then they both would have broken at roughly the same spot at the same time. Or, sorry, they wouldn't have broken. They would have been, if they had a 5 millimeter pin in each one, they would have been easier to assemble. Same pin, put it in two places. But by doing it this way with different pins, they got these stresses to match up. With a 4 millimeter pin here at A, that pin has slightly higher stress. That's going to be the pin that breaks, but it's very close to the pin at B. This allows them to save a lot of material in the manufacture of this product by having these so closely balanced. So I like this answer because it points to a design here that's been well thought out, that it makes sense. It makes sense that we would do that and change those pins that way. So, all right. There you go. There's problem 222.